go ahead and record. All right, so on your graphing calculator, the formula that you're going to see that involves E, there are actually a couple of them, but the main one that you see is this P, it's what I refer to as the PERT formula, and you see that E. So if you look on your calculator, you have and I'm not talking about the letter E that's in the alphabet down below, but yeah, Lily's found it. If you look at where the control key is, I can show you up there too. It's about 4 buttons down from there. So here's control key, and then go to, yeah, it is. It's like 4 buttons down, and you have an E to the X key on your calculator. So just be aware of that when you start plugging in, because that's the key that you are going to want to use. Okay? All right. We are going to talk about the examples. The main examples we're going to do here in the notes have to do with a basic formula for exponential growth or decay. And then there are going to be some other formulas that you'll see in the packet that you're going to do. Okay? What I want you to realize is that the way this formula is written here, it really means the same thing as what I had written for you previously, where we have this y is equal to a times b to the x. So that was kind of the general form that I had given to you before, was this a times b to the x. So a is our initial condition. So a in our formula corresponds to this n sub 0 over here, which usually when you see a sub 0, it's telling you it's kind of an initial condition. So the other issue here is that this formula is being a little bit more precise with the growth or decay here. For our B value, our B is our growth constant or our decay constant. So B is going to be either equal to 1 plus our rate of change, or B is going to be equal to 1 minus our rate of change. Okay, so that gives us our growth factor or our decay factor. Growth or decay factor. Okay, so they're just writing it out in this notation as this 1 plus R. So if you think about it in terms of that 1 plus R, then obviously if we are adding, if R is positive, then we're going to have growth. And if R is negative, then it will be decay. So if we use that particular format, notice that means if we're writing this as a rate of decay, then we would need a negative value there. Okay, so you can think of it as adding the negative or subtracting. So 1 plus a negative rate, or 1 minus whatever that rate is, whichever way you want to think about it. Now, the other thing to keep in mind is when we write our R value, it needs to be as a decimal. Our R value is typically going to be given as a percent. And so to convert it to the decimal form, we're going to be moving decimal 2 places to the left. Correct? Does that make sense? I hope. Okay. All right. Let's look at a couple of examples here. So it says a certain state's population is declining at a rate of 2.6% annually. State currently has a population of approximately 11 million. The population continues to decline at this rate. Predict the population of the state in 15 years. So the other part of this is that if I'm asking you to solve a problem like this, I'm going to want to see what the model is first. So I'm going to want you to have the equation written in like with y's and x's, and then I'm going to want you to go back and actually like plug in. Okay. So if to write the model, we're going to have y is equal to, we need our initial condition or our initial amount, because that's our A value. So what's the initial condition in this case? Piper, what would the initial condition be? Current population of, I'm sorry? The 11 million. Okay. If we just put the 11 there, it's going to make our work a little bit easier, and we just have to remember to include million when we talk units. right? So we're not going to write 11 with all of those zeros there. Let's just put an 11 there. That'll save us a little bit of work. And then times, if it's declining at a rate of 2.6%, then we're going to write that as 1 minus 0.026 raised to the x. If you want to leave the equation written in that format, you can. If you feel like you want to actually figure out what 1 minus 0.026 is equal to and then rewrite that, I don't know what that is. Someone tell me. Y is equal to 11 times, what's 1 minus 0.026? 0.974. Okay. So, woo, I can't write. I cannot write on this thing. That's the hard, even harder. 0.974 to the x power. Thank you, Lily. So take your pick, which format you prefer. But then for this particular problem, now it's asking us to actually plug in. So it's saying we're going to plug in and do 11 times 0.974 raised to the 15th power. So what do we get for that answer? What is this approximately equal to? 7 point, okay, I like that, 7.41. We have got to give all of these problems context. We are not just going to have numbers. That's the other part of the application is we want to include the context, so we need units. So this is 7.41 million people, right? Because our numbers were in million before. Okay. Questions on that? Pretty straightforward, I think. All right, onward. Another state's population is also 11 million people. If this state's population is increasing at a rate of 3.4% annually, predict the population of this state there's a typo there, in 15 years. So try that one for yourselves. We'll go over it in a minute. Okay. Take a look. Don't peek until you've finished. I think most of you have, but some of you may not have quite finished, so don't peek until you check here. Should have gotten about 18.164.
What would you prefer us to round it up as?
Yeah, if you're not, like, sometimes there's going to be context. Like, if you're dealing with money, you know you're going to want to round to the hundredths place, that type of thing. If you're not, then go 2 or 3 places after the decimal, I would suggest. Okay, good question, though. So, yeah, in terms of rounding, 2 or 3 places after the decimal. If it's money, obviously, we're just going 2 after, right? Okay, formula for half-life. It's written a little bit differently in the worksheet packet that you are going to do. In my opinion, the way I'm going to write it here is a little bit easier to understand than the way it's written in the packet. So just keep that in mind. You might want to go back and rewrite the formula. What is half-life? Does anybody know? Have you guys talked about half-life? And, like, I would guess in chemistry you talk about this. No? Okay. So if you notice, like in this particular example, we're talking about a radioactive substance. So most examples have to do with something like a radioactive substance or something that's got some type of chemical in it. And what we're looking at, think about what it sounds like. Half-life, we're trying to determine how long it takes for the potency to be half as strong or half as much. And that's what half-life is. Okay, so that's how, like, when we have a radioactive substance, they've found that the decrease is by a half exponentially, okay? So here's the formula. The formula says y is equal to a, so that's our initial condition, times 1/2 to the x over t. And I want to kind of remind you and explain what each of those parts is, and then we'll look at this example so you can kind of see how it fits in there, okay? So A is our initial amount, just as it is in the other cases that we were just looking at, okay? And then we have X and T, and it's easy to get those confused, so just be careful with this. So X is the time span for which we are looking at a particular element or substance. And then T is the actual life, like what their the half-life time expectancy is. So half-life time or expectancy. Okay. Okay. So let's look at this particular example. It says a radioactive substance has a half-life of 16 years. So guys, that's the T, right? Okay. And then it says approximately how many years will it take 100 grams to digress or decrease to 30 grams? And that didn't get worded quite correctly there, but I think you get the general gist. So this one we're actually just going to set up. We can't solve it yet, but we are going to look at helping us just to kind of see the process of setting this up, and then we'll move on to the other one to actually simplify that one. But let's think about how we would set this up. So our initial amount is how much? The 100 grams. Yeah, so we have 100 grams times the 1/2. That's the decay factor as it diminishes by a half over a period of time. And actually, let's go back. Where does the 30 belong? That's what we want to get to ultimately. So where should that go in our problem? Yeah, it's the y. So let me go back and erase that y and put in the 30, because that's actually where that would go. And then we need to figure out what our x and our t are. And one of these things is what we would be solving for. So it says the half-life is 16 years, and we decided that that's our t. So to set this problem up, we would have 30 is equal to 100 times 1/2 to the x over 16. Okay? And then we have not talked yet, we have not reviewed how you would actually solve this problem. This is an exponential equation that we would have to use logarithms in order to solve. So we're going to come back to this problem when we get to the logarithms right after Thanksgiving break. So you have that to look forward to. Great little segue and reminder about what we have done. So we'll come back to this question on down the road. But let's take a look, and we can actually do the work for this next one. So let's do that one. So it says approximately what percentage of 100 grams will there be in 40 years? So how are we going to set that up? So we're still starting with this 100 grams, and we're going by half-life. So where does the 40 go? Where does the 16 go in our exponent?
40 on top, 16 on the bottom.
There we go, 40 over 16. That 16 is going to stay where it is. Okay. All right, and we need to just plug into our calculator and see what that's equal to. Guys, a very important note. The beauty of your graphing calculator is it'll allow you to do this whole thing all at once. But the tendency sometimes is for you guys to kind of do a little bit of work on your own before you start plugging in, and that's fine. I want you to make a note. 100 times 1/2 to that 40 over 16 power. Guys, this is not equal to, I want to change colors here. Bear with me a second. I want to go bright red. This, it didn't keep. All right, try again. There we go. This does not equal 50 to the 40 over 16 power, right? Think about our order of operations. Order of operations tells us if we have a number that's getting raised to an exponent, we deal with that first, then we multiply. So that 1/2 is the only thing getting affected by that 40 over 16. So we got to do 1/2 to the 40 over 16 power, and then, oh, by the way, we're multiplying by 100. That's what that means in terms of the order of the math, okay? So please be careful about this situation, okay? If you plug into your calculator just as it is here, you should be fine. If you're going to try to do a little bit of math, don't clean it up too much or you might make a careless math mistake. That's the moral of the story on that one. All right, what did we get for an answer on that? Ariana, what'd you get?
71.677.
Okay, let's round that. So 17.68. What would our units be for this? Yeah, per 17.68% of what percentage? So yeah, I guess just 17.68% probably on that. Right? Okay. Not too bad, right? Okay. Okay. I think I'm going to ask you guys to try these yourself on this next page. Please be careful reading. If you look at letter A and letter B, it's kind of it's taking you in little baby steps. So for this first one, it's just asking you to figure out what the growth factor is. Do your 1 plus R. Then here's where they want the model. So a lot of people got confused yesterday because they were trying to do too much all at once, because it's going very slow step by step to kind of walk you through that one. Okay, so that first example is growth. The second one is decay. Try those for yourselves, and we'll go over them in a second. All right, actually, first thing, the exam study guide, I like to give it early. There might be a little bit more that we have to include that I will add to this. I'm looking at an old study guide, and I don't know what we're going to get to timing-wise, how far we'll get. I'll get it. To finish before we end for the semester. So I've given you up to where I think we probably are going to be. There may be a little bit I've got to add to the exam study guide. I like to give it early. I know some people are starting to try to plan. Some people are early, plan early. You're going to be trying to arrange tutoring or something like that. So it's helpful to have that early. So that's why I gave you the exam study guide. Okay? Don't lose it. I have a few extra copies, but not many. If you want to get started working on it, it's great. You do not have to, but like I said, I think for a lot of people, if you can find something to alleviate some of the stress once you get back from break, it's a good thing. All right, check your answers here. So for part A, it was just asking for determining what that growth factor is. And then if it asks for the model, then you better have a y and an x in that equation. Okay? And then it was asking you the 1997 and the 1994 were pertinent to help us figure out what's the length of time that has progressed to figure out what that value is for x, right? All right. And then for this one, we've got decay. It's depreciating, so that's decay. So the growth factor is that 0.8 raised to the x power. So it goes from almost $12,000 in value to $3,000. So yeah, it's kind of crazy. All right,